Hello everybody, this is Dr. C. I'm going to try to keep this pre-lecture shorter than some of the ones we've had recently, so let's just get started. See if I can grab a pen here. It'll let me. Okay, so if you're tired of calculations, this is a part of the course where we're actually going to do some qualitative stuff. And what we're going to try to do here is we're going to try to... Sorry about that, interrupted already. So what we're going to look at is we have a system that's at equilibrium, and we're going to change it somehow. We're going to apply what we're going to call a stress. All right, so you see the word stress here. So Le Chatelier's principle tells us if we apply a stress to a system that's already at equilibrium, the system will adjust in a way that will partially offset the stress. It can't completely remove the stress, but it's going to partially offset the stress. What do we mean by a stress? Most often we're talking change in concentration, change in pressure, change in volume, change in temperature, okay, that will remove the system from equilibrium. So again, it's important that you note the system has already reached equilibrium. We now change something. We add more reactant. We remove some product. We raise the temperature. We decrease the volume. We do some stress. The system will shift. The equilibrium position will shift to partially offset the stress. Okay, let's look at some of these changes. Let's start with concentration. So here's a reaction you're familiar with. This is the Haber process, very important industrial process. The system's at equilibrium. What direction, so we're going to say to the right or to the left, toward products to the right, toward reactants to the left, when we do the following changes. What if we add some ammonia? Okay, so it was at equilibrium. We now add some product. The system is going to shift to try to remove some of what we add. It can't remove all of it, but it's going to shift to remove some of what we add. So how can it remove some of what we add? It's going to shift left. Okay, so if it shifts left, we will make more reactant. And ammonia, we added some. It's going to shift to remove some of it. And I actually have a slide here. Slide. We don't use slides anymore. Let's go to the next. Well, I guess we still call them slides. So this is showing what we just did. So again, the reaction. N2 plus 3H2 going to ammonia. Okay, so we added ammonia. Okay, so here's the addition right here. Okay, so the system was at equilibrium. See? Can you see that? So concentrations were no longer changing with time. System was at equilibrium. We now add ammonia. The system is no longer at equilibrium. It's going to have to readjust. It's going to have to reestablish equilibrium. So we added ammonia. It's going to shift to try to remove some of it. So you can see the amount of ammonia start to go down. Okay, it can't remove all of it. So note that our concentration of ammonia, once we reach equilibrium again, is greater than where we started. My lines keep disappearing. Okay, so it's going to partially offset the stress. Well, note, since it shifted left, my nitrogen concentration goes up. Okay, it's shifted to produce reactant. My hydrogen concentration goes up. Okay, shifted left toward reactants. Now, you'll notice, once again, concentrations are no longer changing with time. We have re-established equilibrium. Okay, so the system was at equilibrium. We added ammonia. We applied a stress that takes the system out of equilibrium. It will then adjust to reestablish equilibrium. In this case, shifts left, removes some of what we add. Okay, let's go back. What if we remove N2? I'm going to write the reaction again. Okay, now we're going to remove one of the reactants. That's our stress. Okay, we decrease the amount of reactant. The system is going to shift to replace some of what we removed. Some of what you didn't remove it, I removed it, but you get the idea. Some of what we removed. I can say that, I think. Okay, and that doesn't look like remove, but that's what that's supposed to say. All right, so we removed some of that we removed a reactant, some of it. The system is going to replace some of that. So it's going to shift left again. So both of these are shift left toward reactants. Okay? So we can add a reactant or product, or we can remove a reactant or product, change the concentration. Okay, hope that makes sense. Now, if you do have a reaction that has a solid in it, and I think one of the sapling questions has one of these, okay? So say you had something like this, okay? We've talked about in class that solids do not enter into the equilibrium expression. So if I wrote Kc for this, it would just be CO2 over O2, okay? So since the solid does not enter into the equilibrium expression, adding or removing the solid, okay, you know, as long as you don't remove all of it, you can't remove all of it. That would then change, you know, that wouldn't be there to react. But if we add some or remove some solid, it's going to have no effect. Okay, no effect on the equilibrium because it's not in that equilibrium expression. Watch for that. I think there's one of the sapling questions that has a solid in it. Okay. Now, the other thing to watch out for in this quiz is that these are all multiple choice questions. And these quizzes are graded very harshly on multiple choice. If you have 3 choices for a multiple choice, if you miss it twice, you're going to get it right on the 3rd time. Okay? So it's going to take off huge amounts of points if you miss it the 1st time and if you miss it the 2nd time. Okay? Essentially, you'll get no credit if you get it right on the 3rd time because you're going to get it right on the 3rd time. All right? So make sure you really know the answer before you submit these. These are not graded like the homework where you just lose 5%. On the multiple choice, you lose a lot. Okay, so we did concentration, add or remove. Let's do pressure. Okay? So what we're going to do is we're going to change the pressure by changing the volume. So say we have this container with a piston. Okay? And we have our gas in here. Okay? Now, don't you love my drawings? We're going to push that piston down, so we're going to really squeeze on that gas. Okay? Okay? So we're going to decrease the volume. All right? So this is just one. We could increase the volume too, but let's say the volume is decreased. What happens to the pressure on that gas? Okay, and we did this last semester, but I think you know. Pressure is going to increase, obviously. Okay? So the system, again, will partially offset that stress, and our stress is an increase in pressure. Okay? So a decrease in volume causes the stress of an increase in pressure on that gas. So the system is going to shift to offset that change. Pressure increases. It's going to shift to decrease pressure. Think through that. Oops, I knew I was going to hit that. Can't write on top of the cursor over there. So we increase the pressure by decreasing the volume. The system will shift to decrease the pressure. How can it do that? How can it do that? We have the same reaction. Okay? Well, if you remember the Pivnert equation, we have pressure and we have moles. Pressure is directly proportional to moles of gas. So if we want to decrease the pressure, decrease moles. Okay? So again, let's step through this really quickly. We decrease the volume. We push this piston down. That increased the pressure. That's our stress. The system is going to partially offset that stress, so it's going to try to decrease the pressure. If it wants to decrease the pressure, decrease moles of gas. Look at our equation. 1 mole plus 3 moles. On that side, we have 4 moles of gas. On the product side, we just have 2 moles. So we can decrease the moles and hence decrease the pressure by shifting to the right. Okay, I'm sorry this is kind of a mess, but these are kind of tricky because there's a lot of stuff going on here. Decreased volume increases pressure, thereby the system will decrease pressure by shifting to the side with fewer moles of gas. Decrease P, decrease N. All right. Now you could go the other direction. You could increase the volume. So let's write this down just to show you can go the other direction. We could increase V, which decreases P. That is now our stress. So the system is going to shift to increase pressure. How can it increase pressure? More moles of gas. Okay, think through that. It makes sense. You just have to think through it. You will see in the first two problems, I think the first part of the multiple choice in sapling is concentration. The last multiple choice question in each of the first two problems talks about changing the pressure, okay, by changing the volume. All right, and the last two questions in the quiz this week is 4 questions, but they're really short. They're all multiple choice. Change in temperature. Okay, now let's just focus on a temperature increase for now, because that's what the two problems in sapling do. We'll do a temperature decrease in class. Okay, which way it shifts will depend on whether it's endothermic or exothermic. Okay, so this reaction happens to be endothermic. We have to break a bond here, break apart N2O4 to get to NO2, so we're going to have to put in some energy to do that. So this is endothermic. Now, for endothermic reactions, think of heat as a reactant, right? Because we have to add heat for endothermic, right? So endothermic delta H is positive, right? We have to add heat to get that reaction to go. So think of heat as a reactant. So we're gonna put it, even though it's not really in the reaction, for our purposes right now, we're gonna add heat to the reaction. Put it on the reactant side if it's endothermic. Now we're going to increase temp. We're going to add heat, add thermal energy. Okay? So let me erase. I'm trying to think where my eraser is. Do I have an eraser? Where is my eraser? I guess I don't. Let's get rid of that. Okay? So I was saying that we put heat on the reactant side because endothermic means you have to add heat to the reaction. Now, increasing the temperature, we're adding heat. We're adding more heat than what was available before. So we're increasing this. Okay, so it's kind of like changing the concentration, changing the amount of heat. The system's going to shift to remove it. So we've added heat, we've increased that. It's going to shift to remove it. It's going to shift right. Okay, so an endothermic reaction, positive delta H, if you increase the temperature, it's going to shift to the right, produce more product. And that will change your K. So temperature, the equilibrium constant is a constant at a given temperature. In this case, because we make more products, K will, let's just say K will increase. Okay, we increase the temperature, system shifts to the right to remove that added heat, produce more product, K goes up. Equilibrium constant is a constant at a given temperature. All right, now, last thing for the pre-lecture. And I wanted to, let's do the same, let's talk about exothermic. If you just happen to have an exothermic reaction, and delta H is negative, just to show you that this is going to go in the opposite direction. Exothermic reactions produce heat. Heat is released. So if it's exo, put heat on the product side. Heat is produced. Heat is released. So now if we increase temp, we add more heat. It's going to shift to remove it. So for exothermic, an increase in temperature shifts it to the left, producing more reactant, and that will change your K as well. All right. So exo and endo are going to go different directions when you raise the temperature. All right. So you will see that in the sapling pre-lecture quiz as well. Now, I just wanted to show you a cool picture. This is that reaction above. This is a nice reaction to follow because our product is brown. Okay. And this is, say room temperature. And this is hot water. Let's just focus on increasing the temperature for now. So we just said, let's scroll back up, endothermic, add heat, increase the temperature, it's going to shift to the right, producing more product, which is brown. Okay, so this is the hot water, and what do you see? This shifted right, okay, toward product. We made more NO2, which is brown. Okay, I still went longer than I intended. I think this is about 15 minutes, maybe a little bit longer. I'd really like these to be more like 10 minutes, but it just seems that I can't get everything done that I think I need to get done. So anyway, do the pre-lecture quiz. They're all multiple choice. It's quick, but be careful. Be careful. They are graded very harshly. Okay? If a three choice multiple choice, if you miss it the first time, you're going to lose half credit. If you miss it the second time, you get no credit because you would get it right on the third try just by process elimination. So watch for that. So make sure you really know the correct answer before you hit submit on those. Okay? The quiz test change in concentration. Watch for solids. They don't impact the equilibrium. Change in pressure by changing the volume. And change in temperature, endo and exo. Okay? Increasing temperature, endo and exo. Watch for all of that. And we will pick up with this in class very soon. See you in class.